Welcome back to The Explainer. Today we're taking a hard, chronological look at the brutal reality of Mars colonization. Forget those romanticized sci-fi visions for a minute, because we're going to dig into the raw data, the massive engineering hurdles, and the immense physiological toll that makes surviving on the red planet literally one of the most terrifying challenges humanity has ever faced. If you've ever looked up at that red dot in the night sky and actually pictured yourself living there, well, you're going to want to pay close attention to the gauntlet we're about to run through.
Okay, let's dive into this. Right out of the gate, we've kind of got to shatter the dream. Here on Earth, we are constantly nurtured by an atmosphere with nearly 21% oxygen, which is perfectly balanced for us. But Mars? It's a deeply hostile, toxic environment composed of over 95% carbon dioxide. Taking just a single breath of that would be instantly fatal. So this isn't just a simple change of scenery. It's a massive transition from a planet that actively wants us alive to a planet that is pretty much actively trying to kill our biology. So here is our mission flight plan for today. We'll start with the myth versus the reality, then look at surviving the deadly transit. After that, we hit a hostile, unbreathable surface, followed by the toxic Martian soil, and we'll wrap it all up with fragile tech and human limits.
Section 1. The myth versus the reality. Before our boots even touch down on the Martian dirt, we have to confront the immense physical distance and the staggering reality of interplanetary commitment.
Think about a standard conjunction class trajectory. Once astronauts launch at month 0, they are looking at a 6 to 9 month transit across 54 million kilometers of deep space. And here's the kicker. Once they arrive, there is absolutely no turning back. Orbital mechanics basically dictate that they have to stay there for roughly 18 months, just waiting for the planet to align again, and that's followed by another 6 to 9 month return trip. We're talking about a multi-year commitment with zero chance of an emergency rescue. Once you leave low Earth orbit, you are completely 100% on your own.
Moving on to Section 2. Surviving the deadly transit. Because honestly, just getting there is a gauntlet that takes a massive physiological toll on the human body long before the crew even catches a glimpse of the red planet up close. In the zero-gravity environment of that long transit, the human body essentially begins to decay. Without the constant, familiar pull of Earth's gravity, astronauts experience severe bone mineral density loss, rapid muscle atrophy, and cardiovascular deconditioning. Now, even with rigorous daily exercise regimens on the ship, astronauts are going to arrive on the Martian surface already physically weakened. Imagine trying to haul heavy equipment and set up a complex habitat in a pressurized, bulky spacesuit while your muscles and bones have basically been aging at warp speed for the last 9 months.
And microgravity isn't even the only threat during the trip. Without Earth's magnetic field acting as a shield, the crew is subjected to a constant, relentless bombardment of deep space galactic cosmic rays. But worse still are solar proton events. These are sudden, violent solar flares that can flood a spacecraft with lethal doses of radiation in just a matter of hours. To actually survive that, the crew requires heavy storm shelters built directly into the ship. They'd essentially be huddling in heavily shielded panic rooms during these solar storms.
Section 3. A hostile, unbreathable surface. Let's assume our crew pulls off a flawless landing. The Martian environment itself immediately begins trying to break both our biology and our life support systems. Now, what's really interesting here is the Armstrong limit. At roughly 6,300 pascals, this is the lowest atmospheric pressure where human bodily fluids won't literally boil. So what is Mars' actual atmospheric pressure? Well, it's paper thin, a mere 600 pascals, which is roughly 1% of Earth's. That means, without a pressurized suit, an astronaut's blood and saliva would boil instantly. And as we touched on earlier, even if by some miracle you could handle that extreme pressure drop, you couldn't breathe the air anyway. The atmosphere is 95.3% carbon dioxide, heavily mixed with trace amounts of nitrogen and argon. It completely lacks the vital oxygen we need. Oh, and to make matters worse, it contains 0.08% carbon monoxide, which is highly toxic. You're looking at a completely suffocating environment from top to bottom. Because of this harsh reality, absolutely everything needed to survive must be brought with us. 200 metric tons. To put that into perspective, according to NASA's design reference architecture, 200 metric tons is the staggering estimated mass of food, water, and air consumables required for just a single 6-person crew on a round trip. Delivering that much weight to the surface of Mars is a logistical nightmare, requiring multiple heavy lift launches from Earth just to get the essentials there. To try and reduce that insane mass, we rely on environmental control and life support systems, or ECLSS, to recycle air and water.
But consider this quote from a Space Settlement Progress Report. Experience with Mir, International Space Station, and Shuttle have shown that hardware failures occur, unreliability of ECLSS. Up on the space station, we can just send up spare parts if a water recycler breaks. But on Mars, our best current life support systems are honestly still way too fragile. A catastrophic failure in one of these complex recycling loops, millions of miles away from any supply chain, is an immediate lethal risk.
Section 4. The toxic Martian soil. The danger out there isn't just floating in the air, it is literally right beneath the astronauts' feet, presenting some truly unique chemical and electrical threats.
Meet perchlorates. These are toxic salts that make up roughly 0.5% to 1% of the Martian dirt or regolith by weight. And guys, this is a massive problem. Just simply tracking this microscopic Martian dirt inside a habitat on a spacesuit could expose the crew to severe thyroid problems. Furthermore, the very soil we'd need to use to grow our food could actually poison it. We would have to extensively wash and chemically treat the dirt before a single seed could safely sprout. Add to that, the environment is bitterly, dangerously cold. Temperatures can actually plunge to an extreme negative 225 degrees Fahrenheit at the polar caps in winter. That is quite literally colder than dry ice. Even the average surface temperature is a freezing negative 67 degrees. This just highlights the relentless, massive energy drain required around the clock just to keep the habitats warm and prevent the crew from freezing to death. A power failure on Mars isn't an inconvenience, it's an absolute death sentence. And compounding the cold and the toxicity is the ubiquitous Martian dust. These are not just your average sand grains, they are ultra-fine, highly abrasive particles that threaten delicate machinery and can easily compromise critical spacesuit seals. Global dust storms there can last for weeks, completely blocking out the sun and rendering any solar power systems utterly useless. Plus, because the environment is so dry, the dust carries a high static electrical charge that poses a severe sparking hazard to computers and critical electronics.
Finally, Section 5. Fragile tech and human limits. So how do human engineers even attempt to solve these compounding survival challenges using resources actually found on Mars?
Well, to build habitats thick enough to block that radiation and insulate against the freezing cold, we have to use local materials to 3D print our shelters. And this brilliantly illustrates the problem, because the trade-offs are incredibly harsh. Extrusion has low energy demands, sure, but it requires us to import heavy water and binders all the way from Earth. Sulfur concrete cures really fast without any water, but the extreme temperature swings on Mars make it highly brittle and prone to cracking. Then there's sintering, which uses lasers or microwaves to melt pure regolith into glass-like structures. Sounds great, right? Except it demands 10 to 100 times more energy. So even our very best 3D printed habitat plans have severe, potentially mission-ending vulnerabilities.
So, what does this all mean? The crucial takeaway is this. Mars is not just a backup Earth. It is a freezing, irradiated, toxic desert that relentlessly wants to break absolutely everything that lands on it. If living on Mars means battling toxic dirt, deadly radiation, and relying on incredibly fragile machines millions of miles from a spare parts depot, are we truly ready to become a multiplanetary species? The sci-fi dream of colonization is definitely inspiring, but the statistical, brutal reality of survival requires engineering miracles we are still striving to invent. It is a fascinating challenge, and I hope this explainer gave you a clear, realistic look at exactly what it will take to conquer the Red Planet. Keep questioning, keep learning, and I'll see you next time.